The Pythagorean theorem tells us that if a triangle is a right triangle, then the sum of the squares of the two perpendicular sides equals the square of the hypotenuse. But is the converse also true? That is, suppose that three lengths a, b and c are such that a squared plus b squared equals c squared. Then, can we arrange these lengths as the sides of a triangle? And would that triangle be a right triangle? The answer to both questions is yes. The angle theta in the figure turns out to be a right angle. This is essentially the converse of what the Pythagorean theorem tells us. In the literature, the converse theorem is usually proved using the Pythagorean theorem itself. The proof is very straightforward. We will prove that theta is a right angle. First, forget about the length c and draw a right triangle with a and b as its perpendicular sides. Let the hypotenuse have length d. From the Pythagorean theorem then, we know that a squared plus b squared equals d squared. But then, comparing the highlighted equations, we see that c equals d. This means that the two triangles shown are equal, and hence theta is a right angle. Furthermore, any other triangle with sides a, b and c will be congruent with these and hence will also be a right triangle. This proves the converse of the Pythagorean theorem. Every time the sum of the squares of two sides of a triangle equals the square of the third side, the triangle is a right triangle. But let us suppose that we do not know of the Pythagorean theorem. Such would be the situation in antiquity, where, for example, the Babylonians, Egyptians, and the early Pythagoreans had empirically noticed that triangles with sides that satisfy the said equation are right triangles. They had even derived formulae that produced triplets of numbers that satisfy the equation a squared plus b squared equals c squared, called Pythagorean triplets. Obviously, they suspected that if the lengths of a triangle satisfy this equation, then the triangle is a right triangle. But could they know it for sure if the Pythagorean theorem was not known to them? Note that, despite the theorem being named after Pythagoras, it is unlikely that Pythagoras himself knew of it in its general form. It was discovered later, as will be recounted in a separate video. In this video, a proof of the converse of the Pythagorean theorem will be presented, which does not presuppose the Pythagorean theorem. In fact, in the end, we will use the converse theorem to prove the Pythagorean theorem itself. We do not, however, contend or even suggest that this proof was known to the ancient Pythagoreans. The proof presented here is based on the one found in the first paper listed on the screen, while another proof was proposed in the second paper. Firstly, let us ascertain that if the lengths a, b and c satisfy a squared plus b squared equals c squared, then they can form a triangle. Since c is the largest length, whether or not a triangle can be constructed is determined by whether or not a plus b is greater than c. If this condition is not satisfied, then the lengths a and b are not long enough to touch each other in order to form a common vertex. So, given that a squared plus b squared equals c squared, is it guaranteed that a plus b is greater than c? The answer is yes. To see it, since a and b are both positive, add 2 times a times b to the left-hand side of this equality to make it larger than the right-hand side. Now, the left-hand side equals the whole of a plus b squared. And taking roots, we arrive at the desired result. Hence, if the lengths a, b and c satisfy a squared plus b squared equals c squared, then they can be the sides of a triangle. So, let us draw that triangle. We suspect that the angle theta at vertex C is a right angle, but we do not know it for sure yet. We begin by noticing that due to the given relationship between the lengths, the side C can be split into two parts, a squared over c and b squared over c. Let point D divide it into such parts as shown in the duplicate figure. We also draw the line CD, which splits the triangle into two smaller ones, CDB and CDA. Next, let us scale the original triangle ABC by a factor a over c, that is, multiply each of its sides by a over c to obtain the new triangle A', B', C', shown in yellow. The hypotenuse of the scaled triangle equals a, whereas that of the original triangle equals c. The sides have become smaller, but the angles have not changed. The triangles are similar. So, angle C of the original triangle equals angle C' of the new triangle, and they are both equal to the sought angle theta. Also of interest is that the angles B and B' are equal. But then we can notice that the triangles CDB and A'C', B' are congruent, because in addition to the angles B and B' being equal, the sides that form these angles are also equal. BC and B'A' are both equal to A, and BD and B'C' are both equal to A squared over C. Since the triangles CDB and A'C', B' are congruent, the angle CDB is equal to the angle C', which is equal to theta. Now, let us keep this result in mind and proceed to do another scaling of the original triangle ACB, this time by a factor of b over c, in order to obtain a triangle with hypotenuse b. This new triangle, drawn in blue, is congruent with the other subtriangle of the original triangle, ADC, because angles A and A' are equal, as are the sides that enclose them. AC and A', B' equal B, and AD and A'C' equal B squared over C. This means that angles CDA and C'' are equal, hence angle CDA is equal to theta. We have therefore concluded that both angles at the vertex D are equal to theta, as indicated in the lower left part of the screen. And since BDA is a straight line, this means that 2 times theta equals pi, or theta equals pi over 2. That is, if a squared plus b squared equals c squared, then the triangle with sides A, B and C is a right triangle. We have thus proved the converse of the Pythagorean theorem. From the converse Pythagorean theorem, we can easily also derive the Pythagorean theorem itself, in a manner very similar to how the converse Pythagorean theorem is derived from the Pythagorean theorem. In particular, let a and b be arbitrary lengths, and let c be such that a squared plus b squared equals c squared. Then, the converse Pythagorean theorem tells us that we can draw a right triangle whose hypotenuse equals c, as shown. Then, forget about c for a moment and draw another right triangle with perpendicular sides a and b. Let its hypotenuse be d, as shown on the right. But, from trigonometry, since these two triangles have their right angles equal and the sides that bound the angles also equal, it follows that they are congruent, and in particular that d equals c. And since a squared plus b squared equals c squared, it follows that a squared plus b squared equals d squared. The sum of the squares of the perpendicular sides equals the square of the hypotenuse. Since a and b are arbitrary, this result holds for any right triangle, which is precisely the Pythagorean theorem. I hope you enjoyed the video. If so, please consider liking it to help with the YouTube algorithm. Thank you.